Hello, my name is Cheetham-West. I want to thank the organizers of this special session for the opportunity to speak. I'm going to be talking about hyperbolic three-manifold groups and finite quotients. I'll post like a link to the paper I'm talking about in the description, and I look forward to having discussions and about this work and about the work of all the other speakers in the Discord channel. So in particular, I'm always talking about groups that are finitely generated and groups that are residually finite. And being residually finite means that every non-trivial element of your group, in this case gamma, has a non-trivial image in some finite quotient of gamma, right? And in particular, finite quotients allow us to attempt to distinguish finite generated residually finite groups from one another. And a good example to think about and keep in mind is the example of z, the integers, right? And if you can see that z is you can check that z is the only finite generated residually finite group to have all its finite quotients be cyclic. Okay, and how do you show that? Assuming you have some other residually finite generated group with all the same finite quotients as Z, one can check by contradiction proof that such a group has to be abelian, and then one can use the fundamental theorem of finite generated abelian groups to see that such a group has to be Z. Okay, and so for a group, I'm always thinking finite generated again. You can think of this set of finite quotients and ask to what extent this set of finite quotients, this list of finite quotients determines G. And this is a well-studied question for many different classes of groups, right? And that motivates a definition. A group is said to be profinitely rigid if it's completely determined by its list of finite quotients among finite generated residually finite groups. Okay, and so we say that the integer z is a profinitely rigid group, right? And so the questions that we can ask is the free group on two generators profinitely rigid? We know what the set of finite quotients of the free group on two generators is. It's like all two generated finite groups, right? And so we're asking, is there a mystery group out there with whose sets of finite quotients is exactly all two generated finite groups? And that's still an open question. We still don't know. We can ask questions about surface groups and the same questions. And restricting also to the class of three manifold groups, there's a fundamental groups of compact three manifolds. It's also a useful thing we can ask. What about three manifold groups? Are they all determined up by finite quotients? Are they determined up to some finite ambiguity? And the question about three manifold groups, there's like better and better answers in that case. All right. And we can work with a list of finite quotients, but it's also helpful sometimes in cases to organize finite quotients of a group into a topological group, into the profinite completion. And what all that requires is for us to consider taking an inverse limit of the inverse system of finite quotients of the group, right? And this is called the profinite completion of the group. It is a finitely generated profinite group. And all that being profinite, the word profinite means is an inverse limit of a system of finite groups. And it's important to check that this profinite completion completely captures the idea of the list. So if the list of groups of finite quotients is the same, the profinite completions are isomorphic. Okay, and so when we restrict to this class of three manifold groups, we see that like finite quotients take on a topological meaning. They're the groups of covering automorphisms of finite regular covers of a three manifold. And so like in a sense, there is a feeling there that something should be captured, that this finite quotient should remember something about the groups, the three manifolds that produce them. And so this has motivated a lot of work within the last 10 years and their results, relative results for three manifold groups. And so restricting to the class of three manifold groups, we get that like if you have the same finite quotients as a hyperbolic three manifold group, if two three manifolds share the same finite quotients and one of them is hyperbolic, the other is, and that's a result of Wilton-Zaleski. If one of them fibers over the circle, the other does. That's like a result of Hyken and Zapirin, building on work of Friedel-Kim, Friedel-Verdusi, and the earlier results of that nature by Bolo-Friedel and Brightson-Reed. And then there's like results of like Brightson-Reed-Wilton, where they show that like once punctured torus bundles are determined by their finite quotients among all three manifold groups. And also the work of E. Liu, where he proves that at most finitely many finite volume hyperbolic three manifolds can share a common profinite completion, right? And so we want to ask this question again for the fundamental groups of hyperbolic three manifolds. And this motivates the definition of a Kleinian group. A Kleinian group is a discrete subgroup of isometries of a three-dimensional hyperbolic space. And the quotient of a Kleinian group is going to be a hyperbolic three manifold up to finite sheeted covers. And when we have a finite volume hyperbolic manifold, we know there's the Mostov-Prasad-GT theorem that says that the discrete faithful representation is unique up to conjugation. Okay, and so there's a unique hyperbolic structure on the manifold, and that comes with the data of a representation into PSL2C, which is 2 by 2 matrices over the complex numbers modeled out by plus minus the identity. Okay, and so asking this question for Kleinian groups is interesting because Kleinian groups are full size in the sense that they contain non-abelian free groups. And so they cannot satisfy laws. We can't like just do profinite rigidity proofs just like we did for Z very quickly in the first like 2 minutes of this talk, right? And so it's a very exciting and groundbreaking result when Brightson, McReynolds, Reed, and Spittler showed the first examples of Kleinian groups that are completely determined among all finite generator residually finite groups by their profinite completions. And for some of those examples, we will talk about the fundamental group of the Weeks manifold, which is the smallest volume closed rentable three manifold, and the Bianchi, the fundamental group of the Bianchi orbifold PSL2O3. So the way they did it was that it was turned into a geometric problem, right? In particular, you have like a group, you have candidate groups, okay, and another group from another construction, and they want to show using the representation, complex representation theory of the first group, which in particular in this particular examples and family of examples is well understood. You want to use the understanding of the complex representation theory of the group they start with, the Kleinian group, in this case G, to constrain the representation theory of any other candidate with the same finite quotients as the group in question. And then more ad hoc techniques using specific properties of the group you start with to restrict this representation and to say that in particular it had the group that you start, the candidate group that you do not know, mystery group with the same finite quotients as G has to actually be isomorphic to G. Okay, and the techniques are very specific to the groups being constructed, but it's sufficiently general to allow one modify the techniques and use them in a variety of settings. Okay, and in particular, it's where I said it was like a geometric problem. You're trying to construct a complex representation of a group that you do not know. and to prove that it lands inside the Kleinian group you're starting with, G, or it lands on the Kleinian group that you started with, right? And in particular, when one is able to get that homomorphism to land, you kind of like land the plane, right? And that process has been made simplified in later work of Brighton Reed, using work of Liu, right? And so here's like a scheme, a diagram representation of this idea. You're trying to, on the one hand, you have this condition of Galois rigidity of the Kleinian group. So the Kleinian group you're proving profinite rigidity for has specific property that it has as few interesting PSL2C representations as possible. So in particular, I'm thinking just the discrete Pareto representation and its Galois conjugates, and that is it. Okay, and then any other properties of the group, like in particular, the group is an arithmetic group, which means that the discrete Pareto representation is tied in with the number theory over the complex numbers. Okay, in a particular way. It's like an honest to goodness, for those who know, an honest to goodness arithmetic subgroup of PSL2C. That will give better control of the representations of the mystery group that we do not know. Okay. And so, building off of this work of Brightson, McReynolds, Reed, and Spittler, like the theorem I'm presenting today is about a family of three examples of like fibered hyperbolic three manifolds with profinitely rigid pi1. And the one example I'll focus on today is the fundamental group of zero surgery on the knot 6-2. So the knot 6-2 is here. A bit of information about 6-2. 6-2, this a genus 2 fibered knot. Okay, and by theorems, I think the easy quickest way, like the zero surgery on 6-2 is going to be a fibered it's going to be fiber over the genus 2 surface. Zero surgery on 6-2 is hyperbolic, and the theorem today is that the fundamental group of zero surgery on the knot 6-2 is profinitely rigid. Okay, so if you take any group with the same finite quotients as the fundamental group of zero surgery on the knot 6-2, it has to be the fundamental group of zero surgery on the knot 6-2. Okay, and what is zero surgery on the knot 6-2? In particular, it means that you are going to be drilling out, okay, this knot from the 3 sphere, and you're going to be capping the Seifert surface, or a Seifert surface for the knot with a disk. Okay, you're going to be capping the Seifert surface with a disk. Okay, and that's how we obtain the zero surgery. Okay? And so for proving this, I said like it is helpful. It is very helpful that the fundamental group of zero surgery on 6-2, which I'm calling here gamma, that it is an arithmetic subgroup of PSL2C. It's arithmetic, and not just as arithmetic, it is it shares a common finite shifted cover with the Weeks manifold, fundamental group of the Weeks manifold, which Brighton, McReynolds, Reed, and Spittler showed is profinitely rigid. But sharing that common finite shifted cover means that it has the same arithmetic information, okay, as the Weeks manifold. And these conditions that I'm listing here, we can talk in detail in Discord, but what these conditions let one do, like having this field of traces associated to the discrete faithful representation of the fundamental group of zero surgery and 6-2, having this this trace field and this quaternion algebra have the specific conditions I think of it as the things that allow us to land the plane for any candidate group, to construct the representation, to restrict the representation that we are constructing using the Beamer strategy. So even though these conditions look technical or are technical, what they let us do, they let us solve that geometric problem of like constructing an appropriate complex representation of a mystery group every time for every possible candidate. Okay, and so we've seen this definition of Galois rigidity, right? And Galois rigidity says that when you have a representation into PSL2C, it is Galois rigid when, in particular, the field of traces of the representation is a number field, and in particular, G has no other extra representations apart from this representation to PSL2C and its Galois conjugates. So in particular, the first condition of the trace field when you start out with a lattice in PSL2C, a finite volume thing, most of rigidity will tell you that, oh yeah, the trace field is a number field. But this extra condition of saying that there are only as few representations as possible, that is extremely rare. And that's one of the limitations of the Beamer strategy. They are more general. The idea is that with extra representations, you have to do more ad hoc things. You need more language, but in particular, having just one Galois orbit of representations makes things work out even nicer anytime you have it. And so for me, in my case, it's important for me to prove that the group gamma with the associated discrete representation, fundamental group of zero surgery on 6-2 is Galois rigid. Okay, and the way I do that is using the fact that it is zero surgery on a knot in the twist field. Okay. And then the next thing that is done is that one proves that for any candidate group, one can again construct a representation, okay, with the appropriate arithmetic information such that the unique index 2 subgroups line up. Okay, and where do we get unique index 2 subgroup from? From the fact that the homology of gamma, the integral homology, the diagonalization of gamma, and any of candidate has to be Z, right? And so we prove that the index 2 subgroup has to line up exactly, and so any candidate has to be a Z mod 2 extension of the unique index 2 subgroup of the fundamental group of zero surgery on 6-2. And so now the problem is changed into an extension problem, right? It's like, okay, just distinguish extensions of that unique index 2 subgroup of gamma from itself. And in particular, we can use the abelianization once more. We can use the abelianization once more and to see that the group gamma is the unique Z mod 2 extension of its index 2 subgroup of squares with integral first homology Z. And in particular, that means that if you take any candidate group, okay, it will have first homology abelianization Z, right? And then it will have an index 2 subgroup that is isomorphic to the index 2 subgroup as to the index 2 subgroup of gamma, and therefore by the lemma above, it has to be isomorphic to gamma. And so the main technique for proving this lemma is an understanding of the outer automorphism group of this index 2 subgroup of squares, and using the fact that like out of the gamma squared out of a lattice in PSL2C is geometric by Mostov rigidity. So these are the many ingredients going into this proof. I look forward to talking to people more about this in Discord in the course of our conference. Thank you all so much for watching, and see you around.